Okay, so as we saw for Newton's third law of motion, basically forces come in pairs, and one force is always acting in the opposite direction from the other force, but with equal magnitude. An example might be, say, if you kick a soccer ball, your foot obviously is exerting a force on the ball, and that's known as the action force. That's the initiating force. And your foot, kicks the ball, and it exerts a certain amount of force on it. Then there's the reaction force. And the reaction force would be like the force that the ball exerts on your foot. And you can kind of feel the fact that the ball exerts a force back on your foot, because when you kick a ball, sometimes it kind of hurts. And that's because the ball is actually exerting a force back on your foot. And so that's an overview of the Newton's laws of motion. Next, we have Newton's law of universal gravitation. And Newton's law of universal gravitation says that every object in the universe is attracted to every other object in the universe to a certain extent. Now, in most cases, that attraction might be very small, but it's there. Okay, and this attraction is directly proportional to the product of the two masses of the objects. Okay, and inversely proportional to the square of the distance between them. Okay, so that's the basically the relationships in the law of gravitational attraction. This force is called the gravitational force. And the symbol is F with a capital G as a subscript. And to summarize what we said up above, because sometimes things like this are easier to understand in sort of a mathematical form than they are in words, when we say that every object in the universe is attracted to every other object with a force that's directly proportional to the product of their masses, what we mean is that F sub G is directly proportional to the mass of object 1 times the mass of object 2. All right. And when we say that that force is inversely proportional to the square of the distance between the objects, what we mean is that F sub G is proportional to 1 over R squared. And R is just a word for radius, which is another term that's often used for the distance separating two objects. So 1 over R squared. When you're talking about gravitational force between two objects, the fact is that that gravitational attraction may not be very great. And so it's often so small that it's not even noticed. You know, I mentioned before that these two pencils sitting here next to each other have a certain amount of gravitational attraction for each other just based on the fact that they both have mass and that they're separated by a certain distance. Now, in this case, their masses are very small. And so mass 1 times mass 2, even when you multiply their masses together, you come up with a very small number. And that results in a very small gravitational attraction between the pencils. It's not even strong enough to overcome the inertia of the pencils sitting there, you know, on the paper. On the other hand, if you look at the gravitational attraction of planet Earth for one of these pencils, all you have to do is drop it and see how fast it falls. And that's because the mass of the Earth is really, really big. So when you take the mass of the Earth times the mass of the pencil, you get a number that's really big. And that's a pretty strong gravitational attraction. And so just as you know, a comparison for some masses, some typical masses. An apple might be maybe 0.1 kilograms, and a person, say 150-pound person, would be about 68 kilograms. And so when that apple fell on Newton's head, supposedly, it wasn't because the apple was attracted to Newton's head, because that mass times his mass would not be a very big number. And so that would not result in a very strong gravitational attraction. The reason that the apple fell on his head was that the apple was actually heading for the ground and he happened to be in the way. The apple was actually attracted to the earth because the mass of the earth is 5.97 times 10 to the 24th power kilograms. That is a really big number. And when you take, even when you take that number times the mass of something small like an apple, that's a pretty significant gravitational attraction. So it really depends on the masses, and we don't really notice that attraction unless the masses, or at least one of the masses, is pretty big. The actual equation for, oh, and also when we say that gravitational attraction is proportional to 1 over the distance squared, what that means is that the gravitational attraction between objects drops off very quickly as they move apart from each other. Okay, so, and for instance, if you double r, the distance between the objects, then f sub g will be 1/4 what it was originally. If you triple r, that is, if you triple the separation between the objects, then fg is cut down to 1/9 what it was originally. So that's a big difference just for a small difference in the separation. The actual equation for gravitational attraction is given as F sub G equals capital G times M1, M2 over R squared. Capital G is known as the universal gravitational constant. It's a proportionality constant, or kind of a fudge factor, if you will, which relates the numbers to each other within the equation, and it also makes sure that the units come out correctly. And numerically, capital G, or the universal gravitational constant, is 6.67 times 10 to the minus 11 Newton meters squared over kilograms squared. And as the name applies, this number applies, and this equation, for that matter, applies everywhere in the universe. Doesn't have to be on Earth. It could be anywhere else. And so another thing to keep in mind is that capital G is not the same thing as lowercase g. Lowercase g stands for the acceleration due to gravity in a particular place. That is not a constant unless you're staying in the same place. But lowercase g varies from one place to another. It varies from one place to another a little bit here on Earth, and it varies quite a bit from one place to another in the universe. But capital G does not. That is a constant. It's the same everywhere. Okay. The universal gravitational constant was actually first devised and measured by Henry Cavendish in 1798, which would be, I guess, 222 years ago. And that's pretty impressive for the day. So that's actually something that's been known for quite some time. Okay. That actually is pretty much the end of chapter 3, or at least what I wanted to say about chapter 3. We can, there of course are a plethora of homework questions for you to work on. So if you have any questions about those, feel free to ask. But for right now, I'm going to move on to chapter 3, because we're only about in the middle of this segment, so we still got a little while to go. Chapter 3 is about energy. Energy is very important in physics because essentially it's energy that allows stuff to happen. Energy changes cause a lot of the things that we see around us in the universe. Energy is also basically the same thing as work. So anytime something gets done, it involves energy. Even when we go into chemistry, a lot of what happens in chemistry is due to differences in energy. When, especially when the starting materials have higher energy than the products, that would be a chemical reaction that would tend to occur on its own without much outside encouragement. Starting off, energy is often defined as the ability to do work. The variable or the symbol for energy is usually a capital E, and the SI unit for energy would be the joule. Symbol is capital J. We'll get around to what a joule is in more detail a little bit later. Well, we might as well do it now. A joule is actually 1 Newton meter. And this is related to the definition of work, which we'll see in just a moment. But remember that a Newton is a kilogram meter per second squared. So if you take that and multiply it by a meter, you get kilogram meter squared per second squared. And so that's actually what a joule is, a kilogram meter squared per second squared. And now you know why they came up with the name joule, because nobody wants to have to say or write that over and over again when you're dealing with energy. 1 joule in units that are more familiar to us is 0.2390 calories, for which the abbreviation is CAL. Calories are considered a metric unit along with joules, but joule is the SI unit and calories is not, even though they're both metric. And so you can use metric prefixes with either of those energy units. You can have, often you talk about kilojoules, because a joule is a pretty small measurement of energy. And so any significant difference in energy at all is probably going to involve multiple thousands of joules. And so kilojoule is a fairly commonly used unit. And you can talk about, you can use metric prefixes with calories also. Kilocalories would be a common unit also. Now, let's see. The calorie is a more familiar sounding unit for energy, but actually it's probably not as familiar as you think it is, because calorie, the unit when it's spelled with a small c, is actually different from food calories, which are normally spelled with a capital C. And in fact, 1 calorie with a small c is 1/1000th of a food calorie. And for food purposes, they kind of redefined the word calorie so that there wouldn't be tons of zeros on food labels. Because, like I said, a calorie with a small c is actually a fairly small unit of energy. Energy is closely related to work, and work is basically what happens when a force either acts or is exerted through a distance. Okay, so that's 2 things that work requires. It requires not just force, but it requires motion. Because something has to change its position so that you can measure the distance that it occurred through. And the equation that's usually used for work is W equals F times D. The symbol is usually a capital W. And the SI unit is the joule, same unit as energy. And here we see how the joule was derived, because remember, the unit of force is a Newton, and the unit of distance in the SI system would be meters. So a Newton meter is a joule. And like we said, a Newton is a kilogram meter per second squared. And if you multiply that by meters, you get kilogram meters squared per second squared. And so that's also another way of looking at a joule. So when 1 Newton of force acts through 1 meter of distance, 1 joule of work is done. that's another way of looking at the equation and how things relate to each other. Essentially, energy and work are pretty much the same thing. I mean, they're like sort of like two sides of the same coin, where work is something that's manifesting itself and noticeable at the moment, whereas energy is usually something that we think of that's being kind of stored up and may not be noticeable, but it's there. And so the interchange between the two is quite common. Work and energy are often changed back and forth between each other. Another term of interest would be power. And power is just the rate at which work is done or that energy is delivered. And I underlined the word rate because it's important to keep in mind that anytime you talk about a rate, you're probably talking about something that involves time. And indeed, that is what we're talking about here. I mean, even if you're talking about something far outside the realm of physics, like an interest rate. An interest rate would be the amount of money, extra money that you have to pay the bank over time, say in the period of a month or a year, in order, for the privilege of borrowing their money. And so even that kind of rate has to do with time. So the equation would be power is just equal to work or energy per unit of time. The symbol is capital P. In the SI unit, well, work or energy would be measured in joules, and time in the SI system is measured in seconds. So joules per second would be the SI unit for power, and 1 joule per second is known as a watt, after the Scottish engineer James Watt, who was instrumental in developing the steam engine, among other things. Okay, so a watt is also known as a joule per second. And so you can think of power units as being a certain amount of energy per second. And so, for example, a 40-watt light bulb converts 40 joules of energy to heat and light every second. Well, every second that it's on, anyway. And so 40 watts just means 40 joules per second. 75 watts means 75 joules per second, and so on. Your microwave is probably like 1,500 watts. That's 1,500 joules per second of energy that's being delivered. There's also another unit of power that's fairly common on large scales. So we're talking things like electric motors or car engines, that kind of thing, and that's the horsepower. In the US anyway, 1 horsepower is defined as 746 watts. And what I put after horsepower is just SAE, That stands for Society of Automotive Engineers, and that's the governing body that set the standard for how to define horsepower in the United States. A horsepower is defined a little differently in Europe. They use DIN horsepower, which stands for German Industry Standards. And in Japan, they use Japanese Industry Standards, or JIS horsepower, which are a little bit different. They're not hugely different from the US definition of horsepower. And either one of these units can be used to represent power for any given object that's delivering or converting energy. So, customarily, like I said, horsepower is used for things like car engines, while watts are generally used for things like light bulbs. But there's no reason you couldn't do it the other way around. You could rate a light bulb in horsepower, and you could rate a car's engine in units of watts. And in fact, since watt is the SI unit for power, many, or at least some of the European car magazines have actually begun reporting the power of engines in the cars they test in kilowatts instead of horsepower. And so it's kind of strange to see that kind of listing there, but if they usually list horsepower also. But if they didn't, you could always figure it out according to this, or according to whatever the German version of this conversion factor is. We have some questions that we can look over that have to do with, say, converting one energy or power unit to another. But we're near the time limit for this video anyway, so I think I'm going to stop it there and pick that up in the next segment. So I'll see you in a moment.